Hi. So this is Michael Bloomberg again, and I wanted to show you. I'm creating a new note for today. There'll probably be a new video every day, but I'm going to explain more about what this is. And as I explain this, I'm going to be putting the book together. So, the central thesis of self-aware networks is NAPOT, or NAPOT is Neural Array Projection Oscillation Tomography. It means that this note that I'm sharing today is located at github.v5ma in the Self-Aware Networks repo. So I'm going to go ahead and show you how to get there. So let's go ahead and open up a new window. So if you go to selfawareneuralnetworks.com, actually I don't remember what it's gonna say. It's not secure, but it's gonna take you to GitHub. Then you click on Self-Aware Networks repo, which is the popular repository right now. So if I go back, you can see, so popular repositories. If you don't see it here, you click on repositories and click on self-aware networks. Okay. So the new note that I'm sharing today is the map. So the maps are going to be different from the rest of the notes. They're going to be part of they're going to be backups for the wiki pages. So if you click on the wiki, you can see there's this, and then if you click on like one of these links, so this one says start.intro.fractal. So if you click on that, it takes you to a different wiki page, which is a collection of, it's going to be a collection of all the notes on fractals, which is important, but I'll have to explain why it's important later. There's a lot of, it's about scaling. It's about how, the part about fractals is it backs up the research that I've done into how how a memory that's stored in this synaptic connections of a single neuron scales to the whole brain. That's an important thing to think about, because if it's true that Hebbian learning is that your memories form when cells I guess the popular phrase, it's not actually from Dahl and Hebb, is that when cells fire together, they wire together. But when we talk about cells, it's like a really tiny little thing that neurons can be really small. And so how is it that a memory at the scale of a neuron can be something that can be activated and retrieved by your entire mind? The memory has to actually scale up. And I have a theory for how that happens, which is like, no one else has a theory for how this happens. So I mean, like, just the fact that there's no one else who has a theory like this, and I've got tons of theories that are completely novel, they just don't exist anywhere else, and that by itself should cause this project to get massive attention. But I still have to explain it to people, so I still have to improve the presentation. And so that's part of what I'm doing with these videos, is explaining exactly why this project should have massive attention. So let me go back to so to get to NAPOT, what you got to do is it's gonna be one of these links, like the start in the wiki eventually. So all the maps are going to be stored in the wiki, but for now, if you go to the Self-Aware Networks repo, which is going to be here, or basically from the main page, you go here. Remember I showed you, and then you go down to you can just scroll all the way down, or see, where is it actually? Scroll all the way down. In the maps, this is map.napot.md, and you can just click on that. And that pulls this up. Another way to do it is you can just go back and you just do Control F on your keyboard, or Command F on your keyboard, and just type in map.napot, and that pulls it up. And another thing you can do is you can go here to search and type map.napot, and then search in this repository. That also will pull up, it will search for what's in the note. So that pulls up this, and so that gets you. Those are 3 ways to get here. Okay, so then this explains what NAPOT is. It's neural array projection oscillatory tomography. So your neurons, they have sensors. They're and think of a neuron as something that has to have it's a sensor and a transmitter, but it's also it considers what's being sent, because there are thresholds for whether that neuron is what kind of transmission that neuron is going to pass onwards. The neuron is firing on a regular basis. It's firing in a tonic way. But if it receives enough signals that overload its activity faster than normal, then it's going to fire faster than normal. Or maybe it's going to be flooded and it will be inhibited from firing. So it may fire slower than normal. Its output can vary in terms of like how many neurotransmitters are released. And this information is covered in my notes, but let me stick to the most important stuff for now, and that's important stuff also. But so NAPOT is a theory from which existing artificial neural network architectures can be adapted to become sentient or conscious or what I call self-aware neural networks. This means that we can adapt the artificial neural networks that are popular today, like deep neural networks or graph neural networks. We can adapt them, we can change them so they become conscious or sentient or self-aware. Sentient and self-aware, those are two different things. Sentient and self-aware neural networks, or conscious and self-aware neural networks. And the theory, what I'm proposing is, what NAPOT is, it is a theory that is going to back the creation of code that, or the code changes we need to make to existing artificial neural networks so that our artificial neural networks become conscious and self-aware like animals or people. And so this theory is exactly for how we can make robots that have internal representations, internal thoughts, feelings, images, sounds, tastes, smells, and animal or human level experiences, and so on. It's not just how the brain perceives its own representations. It's also about NAPOT. It's not just how the brain perceives its own representations. It's also how memories scale from synaptic connections at the cell level to the whole brain. It's also about how information flows through the mind and how it's connected to in the networks of the brain via oscillations. How it goes from oscillating activity into the actual picture of what you see through tomography. So I wrote down neural oscillatory tomography. So I wrote down in the notes, let's see how it differs. So in my notes, I contrast it with deep neural networks and graph neural networks. There's other types of neural networks that I need to distinguish it from. I'm essentially like, part of the idea comes from the Fourier projection slice theorem. Okay, so you notice that neural array projection shares the word projection in common with the Fourier projection slice theorem. That's not a coincidence. That is part of the inspiration for the neural array projection oscillation tomography, the Fourier projection slice theorem. So you can look that up. And so you want to think about this, think about the brain as like, you've got a neural network. There's examples of artificial neural networks out there that are rendering amazing pictures. And those you can look up. If you go on Twitter, you can look up NERF, N-E-R-F, or planoxels. It's spelled right here. GAN synthesis. There's GP3 and GP4. You look at the avocado chair. It's GAN synthesis. That's when a neural network renders something. You can look at neural network interpolation. You can look at point cloud renderings, neural network rendering. And then imagine, so your brain is doing rendering, but not just that. Your brain also has to identify objects and separate what is this object versus this object. How are these glasses different from the environment? That's called object segmentation. And to say all the points that belong to these glasses are glasses, and all the points that belong to this hat is a hat. It's called semantic segmentation, or classification with object segmentation. So we have these concepts, and you have to imagine your brain kind of has to do both operations. Now, it may not do it exactly the same, definitely doesn't do it exactly the same as a 3D semantic segmentation. There's really big differences. But I get into those differences in the self-aware networks. But you can imagine these analogies if an artificial neural network can do 3D semantic segmentation and distinguish one object from another object, then why can't your brain? Right? Which is a much more capable, much more powerful neural network than what's in the computer. So so these links. So this note is primarily a map of links that you can read that are related. Because there are hundreds of notes, and so I've distilled which of the notes are probably the most important to the core topic, the core thesis of my book, which is neural array projection, oscillation, tomography. Or sometimes I just say neural array projection tomography, or neural oscillatory tomography for short. So we've got this note. It's number 149 on 3D phase topology over time, as imagined as tensors in a high-dimensional Taylor series. That's one of my favorite notes. The number 616, and I could probably remove these two. These are just backups of the table of contents. Not that important. It's right now. Later on, so here we go. We've got the self-aware networks, the scope of the book. Conrad explains it. Note number 38, B38, because there's the A series notes and there's B series notes. B38, the nonlinear sequence of actions, just a quote from that note. The nonlinear sequence of action potentials events in neural array projection tomography could be considered as intervals in the Taylor series of polynomials, which is also talked about up there. That's one of the newer notes. See, missing phrase. Here's another phrase: pattern collecting sensor arrays that pass information patterns virtually along specific paths in a conscious entity. So the big part of this is about arrays sending information to others. One neuron array is basically sending out a pattern that other arrays receive. So your eyes, the ganglion neurons in your eyes, they're going to, or in your ears, or in your, those are sensory input areas, and they receive information from the outside world, and that first layer is going to render an array of information, like a TV screen, for the layer behind it. And then that's going to pass on information to another part of your brain, and to another layer of arrays, to another. I'm sorry, I'm sort of using array and layer interchangeably. In deep neural networks, we have layers. In the brain, we have arrays. But basically, an array can be as simple as basically a neuron is projecting outwards whatever it outputs, its neurotransmitters. That's not going to just one other neuron. It's going to an array, because it outputs like a fan. It outputs it's like the inputs of a neuron. It's like there's all these different inputs. That's the dendrite, and the outputs fan out. So it's like the information comes in, it gets calculated, and then it goes out again, right? It's like, it's this branching thing on two ends, and so you have this exit terminal, right? And so when it goes out, it's sending the output of that one neuron is going out to an array, and it's kind of like, I imagine it's like it's creating a signal variation in terms of like what it's sending and how frequently it's sending. That's sort of the quantity of neurotransmitters that it's sending, and it's like the magnitude and the frequency. And there's an inverse relationship between the quantity of neurotransmitters that are being sent and the frequency that are being sent. And the interplay of all the different in the arrays. So the arrays. So you have the first layer, which is your sensory input, and the array that receives that sensory input, and the array behind that is receiving a whole bunch of data from a lot of different neurons in the first array. But I would like to imagine that your brain has to. It's like there is a picture that is being sent to your eyes. It's sort of rendered, and then that first sensor array is receiving that picture, and then it's creating a picture in terms of converting that information into phase signals that have a duration or a magnitude and frequency, and that's sending that information to the next array. So imagine that the first array in the visual cortex is like a it's like the input to a computer screen, and it's like the input to a computer, and then what it sends out to the subsequent array is like the LEDs, is like a TV screen to the next array. And the next array receives that picture, it sees that picture, and then it creates its own image for the array behind it. So it's like imagine an eyeball. Imagine every neuron is an eyeball with an LED. So it sees the information from the previous array, and then it transmits a little LED light to the next array. Now, I'm not saying exactly an LED light, but I'm saying it's a signal, right? You can think of it as an LED light, or like the pixels. Imagine that the neural array is like the pixels on your TV screen, and that's the key idea of pattern collecting sensor arrays that pass information patterns along specific paths. Here we've got tonic waves that set our unconscious expectations. So we have neurons that fire, and then the decay rate of that firing sets causes inhibitory waves to be set, like the timing of inhibitory waves, so that one neuron that fires hits all of the neurons in its exit terminal. So it's like one neuron fires, hits all of the neurons in the exit terminal, and causes them to be inhibited. It changes their timing relative to their regular tonic firing. Now they've been slowed down. And that, if you look at the, how that is going to cause the whole oscillating group of cells to notice. And that's true because of how oscillations work. And that's part of this work that connects to Stephen Strogass's work in his book Sync, is that if you have like a group of fireflies, if they all act as a single sensor together, if one of them, it's the same principle of like if you have two clocks, and one clock, is going to, if it's able to basically send a signal to another clock, eventually the two clocks are going to start to synchronize. They're eventually going to, they can start off in very different, like two metronome clocks. You put them next to each other. Eventually, no matter when you start one versus the other, they start to synchronize. And the same thing is with why do fireflies sort of like synchronize? These are the physics of oscillation. And so the physics of oscillation allow your action potentials to cause inhibitory effects that the whole cell assembly will feel. It allows your cells to basically act as a single sensor. Your body becomes an identified sensor that can basically bind together sensory information on a collective scale, because the incoming signals are felt by the entire network. They're passed along, they're dissipated across the entire oscillating cell assembly. So signals are dissipated everywhere. So there's another note: how to make dog-level sentient neural networks. That's a fun one. It's a newer one. The biggest failure. So I argue the biggest misstep. I should probably change it from failure to misstep. This is a hard argument that might get some pushback, a little bit of pushback, but I think I'm right. So basically, the action potential has been defined as an all or nothing event, which is if you're just considering the amplitude, that's true. But if you're considering the magnitude, which includes the duration, it's false. So the magnitude of the action potential is the amplitude and the duration. And the duration changes. That's backed by research. It's backed by research that's in this repo that I reference. So what happens is your neuron will have, when the action potential goes off, the amount of potassium that's in there will cause the calcium channels to be open for more time or less time, and that causes that changes the duration of the magnitude of the action potential, changes the duration of how long the calcium channels are open, and that will change the number of vesicles that are released. Between the possibilities that you could have 0 vesicles released at some interval of time, like the regular, maybe it's like the regular tonic oscillation is every, I don't know, I don't know if it's like it's like every so often you're going to get a tonic release. There might be one vesicle released. If the neuron gets inhibited, then it's like then 0 vesicles get released. If you get a phasic firing, if you get an action potential, but it's not a high phasic, you might get 2 vesicles released. You might get up to 3 vesicles released if the neuron has a really strong reaction to incoming signals. And so there are different thresholds for the neuron to receive information that determine the magnitude of its response, not the amplitude of its response. So it's not true that an action potential event is an all or nothing thing if you're considering the duration as part of the magnitude. Let's see. There's this note, remember the deactivation of HAL 9000. That's a good note. One called smell conscious representations. This note is kind of abstract. Some of the notes are kind of abstract, which means that if you come across a note where something doesn't make sense, don't throw out the baby with the bathwater. I need to fix this stuff. There's a lot of bathwater that needs to be cleaned up. If you get it, fine. If you don't, look past it. There's one called Tomography from Synaptically Captured Patterns. That's sort of the concept, is that these phase changes that are passed between the neural arrays become part of the tomography of the picture of reality that we experience. We have this multi-layer phase field pattern representation in our brainwave oscillations. Let's see, could it be that patterns gain dimensionality when activated and transmitted? This is an older note that when I was putting together the theory. So some of these notes are like my early thinking that led to the later theories. And see, each neuron. This is not book ready stuff, but these are early notes, and I want to share them because this is an important project. Each neuron in an oscillatory. This really should say each neuron in an oscillating group fires in turn, and this is in reference to what happens in a cortical column. There's some assumption here for me because when I talk about cortical columns, I'm often thinking about the work on cortical columns done by the folks at N.A.P.O.T. There's some assumption that the cortical column is an oscillator by itself, but an oscillator with multiple stages. So I'm an oscillating group. I'm suggesting that a neuron is projecting its phase to an array of neurons connected to its extraterminal. Yes, I covered that. Notes on oscillatory tomography and other topics. It's a good one. Broader representations mean the slower tonic frequency band that has higher magnitude. Okay, so this was. This note contains some references that back up my theory that I found. I'm in a valid sense able to describe myself accurately as a motion picture rendering, a volumetric video constructed from 3D frequencies in a 3D grid. That's a cool note. The human mind is an identified tensor field. And when you think of tensor, think of like vectors in calculus, right? If you have an x, y, and z space, or if you have just have X and Y, right? If you have what is a vector? A vector is a direction, right? And anyway, so it's along those lines. Imagine a 3D space, and you're trying to define objects in a 3D space, okay? And so I'm suggesting that reality is volumetric. That our rendering of reality is volumetric, and that our rendering of feelings and emotions and everything that the mind thinks about can be adapted to this volumetric representation of reality. And it's how we relate to other people and to animals. There's this sort of like Animals have volumetric representations. That's how they navigate reality. They have to have a sort of mental map of their environment in order to navigate. And a related idea to NAPOT that I came up with after NAPOT is COT, or cellular oscillating tomography, because it turns out that the receptors in every single cell have thresholds for firing, just like the action potentials. Your NMDA receptors have thresholds for firing, so they have to consider 4 levels of conductance to determine their response. And then if you the same sort of, like, when I was going through NAPOT, I realized, well, synaptic connections, when they change, that is your that's your LTP or LTD growing, or when your synaptic connections grow, that you're establishing memories that are represented in the physical change of the cell, because that changes what the cell is going to respond to. That changes what the cell is sensitive to. That changes what activates that cell, and therefore the physical structure of the cell, as represented by synaptic connections, is a memory, because that physical structure is like, well, what does a memory mean? A memory is what I, like, if I need to remember what sunglasses are, I first have to have a representation of sunglasses in my mind, so that when I see sunglasses, I will have that memory, and that will so that synapses are basically an advanced data structure, or an expert. I like to call it an expert data structure. And so, yeah. So and let me keep moving on, because there's a lot to cover. The high frequency action potential will knock the high frequency brain waves the hardest. So the beta waves will precede the alpha waves. Okay, so this one is okay. This one is a little bit hard to understand, but it's true. But when it's probably too early to include that. This is more advanced stuff. Yeah, I have to go into that later. You can look at it though. Maybe you'll get it. If you're a neuroscientist, you might get it. Okay, so the mind is like a rendering. Even the non-visual parts in that rendering, it's a frame, like a movie. Let's see, neurooscillatory tomography. I want people to think about holography, like holographic images, but it's not holography, it's tomography. So when I say tomography, I want you to imagine like a hologram, right? But it's a tomogram. It's like your mind is making tomograms from phases. Our brains are rendering representation of reality and ourselves with computed graphics. And a set of neural arrays are passing phase patterns that represent learned data that is rendered to the next array. Again, like every neuron is like an eyeball with an LED on it. It's passing a rendered representation of reality to the next layer. So you're seeing tomography, not holography, but I want you to think about holography. You're seeing tomography of your brainwaves when you see anything. Reality is rendered in the phase variances of your brainwave activity. It's not you that's seeing anything, it's your neural arrays. The layers in your cortical columns, the observers, are the oscillating groups of cells, the neural circuits, the cortical columns, and any oscillating cell assembly defined as a body of synchronously firing cells. Each neural array is seeing part of this picture, and in time, the parts of the picture are bound together in your volumetric experience of reality. So this next series of notes that's included in this note is called the flow of information in the brain, from the incoming senses to the motor outputs and everything in between. This is a small selection of the notes that I've made on the flow of information in the brain. This is the main one. It's a conversation I had with a brilliant neuroscientist. We talk about how stuff comes in from the incoming senses, where it goes after that, from your eyes along the optic nerve to the thalamus, to back to the occipital lobes, and up to the parietal lobes. The visual activity. There's all these different. We talk about it's not just from the thalamus to the V1 that goes from the thalamus to the V2, and then both and there's feedback loops back, and then there's all this, like, there's a lot happening in terms of like how information is moving around the brain. We cover a lot of that. I'm going to keep going. There's a ton of stuff. But I'm going to keep going. So because we're going to sort of we're skimming over stuff today, but there's more to come back and dive into more deeply later on. Our brains are basically rendering 3D objects, but from incoming senses. So a line is a rendering in a 3D environment. Wait, so the line is a rendering. So line is rendering a 3D environment. Some of these, they start with B, were audio notes, and I do need to go back and fix them because they were transcribed by a neural network, and the neural network would replace some of the words, and so they have to be fixed. And sometimes there's misspellings, and sometimes I just repeated myself too many times in the audio. See, there's excitatory neural pathways from incoming senses. Each phase interval represents a vector. I later revised that to a tensor because we're talking about a volumetric representation. The key thought about where the observer is inside the mind, where the person is inside the mind. So we know, like, we talk about your brain is, we talk about the neural correlates of your experience. Like if you look at Jack Gallant's work, he says, okay, well, he has someone sit in an MRI machine and they watch a movie and they see different parts of the brain light up, different activity patterns, as indicated by the data in the MRI machine. So there's neural correlates to what you're seeing. But the question is, if your brain is making models of reality with neural correlates, where's the observer? Where's the man inside, the eyeball inside, the third eye that's seeing what your brain is modeling? And my suggestion is that it's the neural arrays. That's what NAPOT means. It's the neural array projection oscillatory tomography. Each of your neural arrays is seeing part of the picture, and through oscillation, those different parts of the picture are bound together. So the flow of information in the brain, it's important, but it's about, you imagine that as information flows through the brain, we cover this topic, through the neural circuits. Here, this is research that says, the flow of information in neural circuits is primarily regulated by modulation of synaptic efficiency. I didn't write that sentence, I found that sentence. But what it means is that the modulation of synaptic activity efficacy, the modulation of synaptic efficacy means that your synapses can be inhibited, or they can spike in higher. There's a tonic frequency, there's a phasic burst, there's a high phasic burst, and then there's an inhibited signal, and that can release either 0, 1, 2, or 3 vesicle sacs, and that determines like whether the downstream neurons are going to receive signals to be inhibited or excited, and they are going to respond to what they're receiving based upon their synaptic connections, which is your memories, your long-term memories. There's more notes on the flow of information in the brain. The flow of information is neural circuits that are primarily regulated by the modulation of synaptic. I already went over that. Do I have that? No, okay. Apparently, we're transmitting virtual portraits, meaning information about both sensory data and motor data all over the brain through the neural networks at a high level. It's one of my audio notes that was more speculative, and at the time that I said it, it was very like, I was like, is this true? And then later on I was like, whoa, that is true. Yeah, it's like we're transmitting sensory information all over the place. It's actually rippling, and there's evidence for that. So, not in this note, but there's evidence for information being sent all over the place. That's in this repo. I began you would look up ripples, look up rippling and ripples in this repo, using the search box that I showed you earlier. So I began to realize there are cycles and feedback loops. This is an old note. At every level, from backwards, propagating action potentials to dendritic arbors to neural circuits. I think that note's from 2014. Some of these notes are super old, but I included it because it's still relevant. Because if you go back to like the top of this, the flow of information in the brain, the interview that I had with the dialogue that I had with this amazing neuroscientist, that sort of like backs up. We dive into, yeah, there are feedback cycles. The whole brain is all these feedback loops, and that really dives into like Douglas Hofstadter's book, Gödel, Escher, and Bach, and a strange loop. I'm a strange loop. You have the feedback cycles of neural activity for the rise of the strange loop that Douglas Hofstadter talks about for the conscious feedback loop. That's in your brain. And see, at the meso level, we're exploring changes to neurocircuits and cortical columns, and at the macro level, so again, this is about some of this stuff is like, well, how does you action potential sequences that fire that represent incoming sensory information, and then they create the neuron has the sensor arrays, and then it takes it into the neuron, it calculates the phase change, and it broadcasts it out like I went over earlier, and that is the explanation for how it goes from how you have a small synaptic memory that a neuron responds to because it has a specific, it's specifically paying attention to certain things because of its synaptic memory configuration. And then when it broadcasts out, it scales up that pattern from one neuron to the whole brain through the inhibitory waves. Through the inhibitory wave is going to change the inhibitory neuron path, the bifurcation of the signal in the inhibitory neurons, and that's going to change the representation that you're perceiving. And then here we go, we've got, let's see, the passive information flowing to certain, I originally wrote holographic patterns, but I really mean tomographic patterns that represent a perspective on space-time. And now, I also compared this to deep neural networks because this is self-aware neural networks is real technology that's ready to be, it's the theory that we can use to change existing artificial neural networks, like deep neural networks, into conscious or sentient self-aware neural networks. And so we have, to back that up, I talk about synaptic unreliability, which is based on the all-or-nothing principle, which I argued earlier was incorrect. And it's a foundational concept, but that's still being used in deep learning today. So that is one of the ways that self-aware neural networks are different from deep learning. I go more into the evidence for the synaptic unreliability article. Potassium, it's really, this is about when I was explaining that potassium modifies the action potential amplitude, but really, this is actually need to change the action potential magnitude, the action potential duration. So this is an incorrect statement that I need to change this to duration or to magnitude. But the idea is right. It's just worded incorrectly here. So each array is a complete deep neural network. Okay. Some of this stuff needs to be fixed. But I'm trying to, like I need to say, imagine each array is like a complete deep neural network, okay? Or like a grid network or a graph neural network. And it's designed so that video frames pass through the entire mind. Imagine that what people call deep learning is neurocircuits connecting together, temporal spatial patterns, and making predictions about future inputs. Like I said, there's lots of stuff that needs to be fixed. That's somewhere along the lines of what I've been talking about, but it's not exactly phrased correctly. The major goal of a deep neural network is to achieve a compressed and accurate representations. I still agree with that. I'm at WeWork, so people are going to be walking by, and you may hear noises. But let's see. So imagine you are like a cycle of neural coincidence patterns connected by a process similar to what people call deep learning. But your neural circuits connect together temporal spatial patterns and make predictions about future inputs. That sounds like an earlier one. See, what is it? It's part of what makes it different from neural networks. There's a multimodal aspect, and deep learning, we'll get there with deep learning. Deep learning has multimodal neural networks. There's, for a long time now. Like you can combine like the recursive neural network with the convolutional neural network. You can combine, you know, basically a neural network that's focused on visual information and a neural network that's focused on audio information, and you can have, you know, cross training between different modalities. That's not the core feature, but I can't imagine someone trying to like. You can make a sentient self-aware network that's modality selective, but it's going to be better if you have if it's a multimodal neural network, self-aware neural network, because when you combine the different sensory modalities of, you know, mechanical sensors and hearing and smell and vision, and, you know, all the different sensations, there's cross pattern learning, and that develops the your representations of reality more thoroughly, right? So, I mean, yes, there's no strict, like when we make these self-aware neural networks, you don't have to, we can add modalities and we can subtract modalities. You can have new kinds of sensor perceptions that don't exist in the animal kingdom. Let's see. So neuron array synapses, it's integrating lower level patterns at a higher level, it's feature learning and deep learning. Okay. Let's move on. So self-aware neural networks are very different from graph neural networks that render screens to themselves, because the rendered representations are separate but also interlinked. Imagine you're looking at like a video editor, like Adobe After Effects or Premiere, but in 3D, and you have multiple layers, and you can link these different timelines. Like each layer is a different like timeline, and you can link them together in higher dimensions, so that if you have a turtle in one part of one movie that's in one layer, and you have a rabbit that's in one part of one movie in another layer, the rabbit and the turtle can meet in your mind, even though they might be in different parts. And it's like, so I'm suggesting, yes, that you have, in a sense, that these layers are maintained in active brainwave activity oscillations. They might be alpha oscillations or theta oscillations. And so if you get new input, the turtle's behavior, which might be a response to a sequence that's in your mind, links to your motor output. The turtle's new behavior. So you might get new input. The new input might be a change in the turtle's behavior. And that might be a response to a sequence that came from your motor output activity. Like you did something with your hands, the turtle responded, your brain noticed that your hand movement caused the turtle to do something. Your brain noticed internally, right? So we have, that was like redundant, right? So we have multiple neural circuits running concurrently and possibly in patterns that are separate from one another. I'm arguing that our brains are making a computer program. It's a computer program, and it's about this is one of those like a neural tomography, but this is like the audio. This is an audio note. It starts with B, and so the AI replaced neural with narrow. See, that's what I mean. The AI replaced some of my words, and that's why I need professional transcripts that will help me get this book done faster, because I have to go back and like manually fix this stuff. But like neurofunctional tomography sensor input. Anyway, so it's important. The phasic and tonic relationship I kind of already described. There's a tonic rate of firing, and there's action potential spikes, and the tonic frequency rate is set by the decay rate of the action potential, or the duration of the action potential, which is set by the quantity of potassium. And that means that the neural circuits can track or be aware of, or respond or speak back to other neural circuits. That's another interesting note. So notes on scale, inhibition, magnification, fractals that are related to synaptic memories, and scale to the whole brain. So how do memories at the synaptic level scale? How do they get bigger? LTD, or large-scale inhibition patterns. That's how. From neural circuits in proximity to a neuron's phasic spiking event. I've described this already in this video. But traveling through these patterns, or traveling through neural circuits, so we have an inner voice. So this one was about describing how our inner thought, like the inner dialogue, or even my exterior dialogue. When I speak, there is a sequence of activity, brain activity that's firing, that's causing the muscles in my larynx and my voice to activate, to produce sequences of words and vowels and different sounds, right? And this is like neural activity that's causing these muscular changes. This is motor outputs. So the motor outputs are causing my voice and my words and my fingers when I type. And so traveling through these patterns, basically, our neural circuits are, as activity flows through the patterns of the motor output in different sequences, that evokes different sequences of movement, different sequences of movement in the larynx. Fix the representations collected by other neural networks, but also add to them, like display. I describe the oscillator as being many layers, like Photoshop layers, but these are layers of interlinked renderings. So the cortical, like there's a lot to unpack there. I'm going to skip over for now. But it has to do with, like, the oscillator is essentially the perceiver, the oscillating group of cells. Like, a neuron is the sensor, but it's the group that's perceiving. The group of cells that are oscillating together is what's storing the memory. And this is important because that neuron could be inhibited from firing when the new pattern comes in and some other neuron has to respond to it instead. And that's possible because it's actually the group that's learning the memory, the group of cells. So any part of that group can receive the signal, and the rest of the group can react to it. And in fact, they do physically react to any pattern that they receive as a collective, like the fireflies in the book Sync by Stephen Strogatz. And I think that neurons detect coincidence patterns and make direct inferences to build spatial and temporal representations within neural circuits. This is right. My research is right, and there's like tons of references that backs this up. It's not, and this is not just my research. I'm putting together a lot of research that other people did, but it's right. We're going to build sentient robots. This causes neural networks to fire in sequences like the lines on a TV screen that is seen by the oscillator itself, because each neuron is mechanically listening to other neurons. When I say that each neuron is mechanically listening to other neurons, a neuron is physically reacting in a mechanical way to the signals from the previous array of neurons. And phasic firing of neural circuits in multi-level fractal patterns. There's a lot to say about fractal patterns. You can read that note. I need to go into that topic another time. It's a very big topic. This note drives home how our rendering in neural circuits can become conscious qualia in the human mind. Yeah. The entire neural circuits, that's this note right here, B0100. Entire neural circuits simultaneously, because exoterminals branch radially in every direction, in every possible direction they can go. So, again, I need to fix some of these statements, but this was about how a neuron broadcasts its output to a whole array that receives that output, like an LED that on a TV screen that broadcasts its output to the whole room. Okay, the nerve circuits, the layers, the cortical columns, they transmit their learned patterns to every part of the brain, which builds multimodal models of incoming patterns. Transmit to every part of the brain, which builds multimodal models of incoming patterns. Yeah, so it's like your ears are receiving patterns, and your eyes are receiving patterns, and your mouth is receiving patterns, and each one of those things is a sensor modality, and then those are received by your brain, and they get transmitted, and they link together, and so you can combine what you hear and what you see and what you touch, and you can say, oh, that's what I touched, and I heard that sound, and I saw my hands clap, and that's what that means. Basically, your neural circuits receive the information, your brain combines them, because And your brain can combine them because the signals are being transmitted across the brain. They're rippling across the brain. Going through these neural circuits in a cortical column will go through like sequences of oscillatory firing. And they're going, and the rippling goes to every, basically, like rippling signals go to every neuron. They alter the timing of every neuron. Like a group of fireflies. Your brain is like a single sensor. Your whole body is like a single sensor that is sensitive to anything it can sense. And then those signals percolate or oscillate and bind through oscillation into tomography, oscillatory tomography of the signals being received by the single sensor. And so the neural circuits, the layers, the cortical columns, they transmit their learned patterns to every part of the brain, which builds the multimodal incoming patterns. We went over that. Goes through these, the neural circuits in a cortical column would go through like sequences of oscillatory firing. It's a multi-stage temporal spatial firing event. Yeah, temporal spatial, see, and then that's the neural network will replace spatial with spiritual. That's not supposed to be there. It's temporal spatial phase patterns percolating through neural circuits that are matching our signals from in our left and right hemisphere, even after the corpus callosum is cut. So that's saying, like, in split brain patients, if you still have synchronous activity between the left and right hemisphere, there are other pathways, not just, like through the thalamus, through the thalamic ridge, between the left and right hemisphere. But it doesn't, like, if things, let's not go into this. There's cool stuff to know there, but we're just going to finish this. Temporals, we already went to that. So that means your thoughts are in the neural circuits and in the local micro columns, in the cortical columns, and in the little clusters of cells. This is the end of this video. Thank you very much for watching, and I hope you enjoyed this map of some of the notes that are connected to this core thesis, this central thesis of my book and the Self-Aware Networks Institute, which is called NAPOT, Neural Array Projection Oscillation Tomography. It's how your brain sees your models of reality. It's how human consciousness works and how we can build sentient robots that are conscious just like you. Thanks very much for watching.